Hey guys, I'm trying to be one of those guys that doesn't start every video they ever do by saying, hey guys. So just so you know, the fact that it just happened is kind of a big deal. Also, just so you know, I just sneezed. In the process, I bit my tongue really hard. So this video is not off to a good start. I'm sure you're thinking the same thing. Let's talk about graphing reciprocal functions. This is also called hyperbolas. It's where you have an x on the bottom and numbers on top. So it's not quite a full rational function where you can have variables and expressions on top and bottom. It's a bit more simplified where we'll only ever have an x on the bottom and maybe some multipliers or adders around that. Think about what happens as x gets bigger. So for example, if x is 0, we know that 1 divided by 0 is undefined. So we actually can't graph the point x equals 0. If x equals 1, 1 over 1 is 1. If x equals 2, we get a half. And if x equals 3, we get a third. These points look like this. As x gets bigger and bigger and bigger, this gets smaller and smaller and smaller, and it keeps approaching 0. This is what we call an asymptote. An asymptote is a line that your graph continually approaches out on the extremes. You might have heard in the past that an asymptote is a line that your graph never touches. We're going to see in our next video, there are actually cases where a graph can touch an asymptote in the middle, like towards the x-axis and towards the y-axis, but not out here in the extremes. So for now, just think of an asymptote as a line that our graph continually approaches. But what also happens is if I plug in numbers between 0 and 1. So for example, if I plug in a half, well, 1 divided by a half is actually 2. And 1 divided by a third is 3. And 1 divided by a tenth is 10, and 1 divided by a millionth is a million. And you'll recognize as this number gets very small, this gets very big. So you can put in a half, you get 2, a third, 3, a quarter, 4. This graph goes like so. It has two asymptotes, a horizontal asymptote and a vertical asymptote. Graphs like that. This little bumpy part, hurts my soul, but here we are. Two asymptotes, an asymptote, a horizontal asymptote at x equals 0, and a vertical asymptote at x equals 0. I say x equals 0 twice because this first one should have been y equals 0. So in this case, the x and y axis act as asymptotes. The horizontal asymptote is the x-axis where y equals 0. The vertical asymptote is the y-axis where x equals 0. Let's do the same thing with negative points. Everything just switches. So the point -1, -1, -2, -1/2, -3, a third, quarter, fifth, sixth, seventh, -1/2, -2, -1/3, -3, 4, 5, 6. And here is my pretty hyperbola. A hyperbola has two asymptotes like we just discussed. One here and one here. But it also has some symmetry that I think is really cool. So there's symmetry here. If you reflect over the line y equals x, 1/2 folds to the other. And there's symmetry here. If you reflect over the line y equals -x, they'll fold over each other. And you'll note that all four of the lines that I just graphed intersect at the origin. That's just the case because this is the parent function, the very, very simple, basic version of the function. We'll see other versions as well. So note, the domain of this function is all real numbers except 0, which means the range of this function is all real numbers except 0. Okay, let's get more exciting. I know you're thinking, how can we possibly get more exciting? But now we've got a multiplier. You can think of this as 2 times 1 over x. So here's our parent function, and it was dilated by 2. It has a vertical stretch by 2. Notice how what was the 0.11 is now the 0.12. Okay, so the purple graph is y equals 1 over x. The red graph is y equals 2 over x. All the y values got doubled. And it's very hard to see any difference that makes in an area like this, where the y values are so close looking to each other. But here you can see that got doubled, that got doubled, that got doubled. All the y values are getting doubled. This is y equals 2 over x. has the same asymptotes. X can't be 0 and y can't be 0, but the values are all doubled from the previous one. We'll do one more before we start talking about the general form of these reciprocal functions. This graph is going to be just like the one we just saw on the previous slide, only this shifts everything to the left 3. The transformations we've learned about don't change. We still have a, h, and k. I still think I'm best off by making a table. And in the table I have to think, what can x not be? In this function, x cannot be negative 3. If I plug in negative 3, I'm going to get out undefined. I'm not going to get out 0, I'm going to get out undefined, which means I have a vertical asymptote here, because x can't be negative 3. Some numbers bigger than negative 3. I'll do negative 2 and negative 1 and 0, but I'll also probably do negative 2.5 because it's really close to negative 3. If we plug in negative 2 for x, negative 2 plus 3 is 1, and 2 divided by 1 is 2. So you plug in negative 2, you get out 2. If you plug in negative 1 for x, negative 1 plus 3 is 2, and 2 divided by 2 is 1. So you plug in negative 1 and you get out 1. If you plug in 0 for x, 0 plus 3 is 3, and so we have 2/3. 0, 2/3. This is going to keep going closer and closer to 0 as we go to the right. If I plug in negative 2.5, well, negative 2.5 plus 3 is a half. So I'm doing 2 divided by a half, which is actually 4. Take the reciprocal, that's really 2 over 1 times 2 over 1 again. If I plug in a half, I get out 4. If I plug in a third, I'll get out 6. So, I'm sorry, I can't plug in a third. I plug in a third away from negative 3, so negative 2.6 repeating, and I'll get out 6. Come on, pretty graph. Good. It's going to be okay. Your graph is going to look like it's touching the x-axis because it has to. Eventually, you get so close your eyes don't see the difference. Just don't ever let your graph drop beneath it if it's not supposed to. Like I said, in our next video, we'll see cases where it does actually drop beneath and then come back to it on top. But that's not today. Okay, I just plugged in negatives. Let's plug in let's get less than negative 3. So I just did, this was all greater than negative 3. Let's do numbers less than negative 3, like negative 4. If I plug in negative 4 plus 3 is negative 1. 2 divided by negative 1 is positive negative 2. That's right, positive negative 2. It's my favorite number, positive negative 2. If I plug in negative 5, I'm going to get positive 1, positive negative 1. And I'm going to have the same pattern that I had before. Whoa. I'm going to have the same pattern that I had before. Graphs like this. There is a horizontal asymptote still at the x-axis. That line wasn't great. There's a horizontal asymptote still at the x-axis. So our domain is that x cannot be negative 3, and our range is that y cannot be 0. Everything appears except for those two values. And maybe you're curious to find the symmetries again here and here. Those are two lines of symmetry that are pretty sweet. Okay, for hyperbolas, here is the parent function, y equals 1 over x. The center of this graph is at 0, 0, but you'll note 0, 0 isn't actually a point on the graph. Like when the graph graphs like this, 0, 0 doesn't actually appear. There's a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. These are lines, equations of lines, x equals and y equals to make them lines. We can add a dilator, a horizontal translator, and a vertical translator with a, h, and k. A is the dilation, and if a is less than 0, then the graph reflects over the x-axis. H and k is the center of the graph, which again is not actually a point on the graph, just the center of it. And the vertical asymptotes are at x equals h and y equals k. So for this example here, our a value is 2, our h value is negative 1, and our k value is 3. That means the center of this graph is going to be at negative 1, negative 3, because k was negative 3. Negative 1, negative 3 is here. Here's the center. There's going to be a vertical asymptote at x equals negative 1, and a horizontal asymptote at y equals negative 3. And that's the graph. So this one's already graphed for us. We can find the asymptotes, find the dilation. It was translated. If we want to write out the transformations, it was not reflected. It was dilated by a factor of 2. It was translated left 1. I'm sorry, I'm writing so fast. And down 3. I'm trying to write fast to make the video shorter, but makes my writing messier. And it's just a lose-lose for all of us. Oftentimes the term dilated is called a vertical compression or vertical stretch. In this case, it was vertically stretched by 2 because things got farther away from the y-axis as opposed to closer to the y-axis. Okay, so let's just do one last one. This hyperbola has an a value of -3, an h value of 2, and a k value of 1. That means the center of this hyperbola is going to be at the point 21. So that point 21 is not actually on the graph, but is the center of the graph, and through that point, I have asymptotes. There's going to be an asymptote here and an asymptote here. So I could now state that I've got vertical asymptote at x equals 2. Why? Because x can't be 2. I know it's kind of weird, but since x can't be 2, that's where the asymptote is at x equals 2. The horizontal asymptote is at y equals 1, because that's what that number is here. So here is the line y equals 1. Here is the line x equals 2. If we think about the transformations in advance, it's going to be reflected over x-axis, dilated by 2, and then translated right 2 up 1. So now what we're going to do is actually just graph the function, right? We've done all this work. We have to actually make a graph. It's going to look something kind of like this. No, that's not true. Because it's negative, it's going to look something like this. But you can't just do that. You can't just draw out the sketches. Let's plug in a few points and find a few values. I want to plug in numbers around 2 because 2 gets me undefined. So if I plug in 3, -3 divided by 1 is -3, plus 1 is -2. So I have the point 3, -2. If I plug in 4, 4 minus 2 is 2. I'm plugging 4 in for this. 4 minus 2 is 2. -3 divided by 2 is -1/2. Sorry, -1.5, -1.5. -1.5 plus 1 is -0.5. Let's plug in 5 for good measure. 5 minus 2 is 3. -3 divided by 3 is -1. -1 plus 1 is 0. And it's going to just keep getting closer like this. The other side will just be a perfect reflection. So if you wanted to start like counting points over, yes, I could plug in 1 and do the math, but I could also say this point is going to go up 1, 2, 3, and left 1. So left 1, 1, 2, 3. It's going to be right there. I can start like counting points to figure out other values. This is up 1, right 1, 2, 3. Yeah, up 1, right 1, 2, 3. So I can go right 1, 2, 3, and up 1. I can find points that way if I want to. Just use the symmetry that I know exists. Or we can just plug things in. So for example, if we plug in 0, let's plug in 0. 0 minus 2 is -2. And -3 divided by -2 is 1.5. 1.5 plus 1 is 2.5. So this is 0, 2.5, which is right here. We get the idea of how this works. I'm going to just sketch out the rest. So that symmetry trick about counting points, you can say from this point to the center. That's what I was counting. I should have made that clear. From a point on the graph to the center was up 1, 2, 3, and left 1. So if I go left 1 and up 1, 2, 3, there'll be a point right there. To recap, hyperbolas are the reciprocal function where the variable x is in the denominator and not in the numerator. Hyperbolas have vertical and horizontal asymptotes, and symmetry is about the intersection of the asymptotes. So if there's asymptotes there, there's symmetry here. In our next video, we'll discuss rational functions where there's variables on top and variables on the bottom. These can have horizontal and vertical asymptotes of different amounts. I guess just one horizontal asymptote, but they can have multiple vertical asymptotes. So let's get excited about that one. I guess hyped is the term you kids use. Let's get hyped.